Alright, welcome back to episode 1 of the Projectile Motion series. So, in this is going to be the first episode where we write some code, but before we do that, I want to explain the idea behind the simulation. So first, I'll just draw a little diagram for a standard projection motion problem. We have some angle theta to the horizontal, and let's say it's a ball, and it's thrown at that angle to the horizontal at some speed v. That's a nice v. Alright, and in this episode we're going to ignore air resistance. We'll add in the air resistance part probably in the next episode. So with this, we know that the initial speed in the x direction, which I'll call vx naught, will be given by v cos theta, and the initial speed in the y direction, vy naught, will be given by v sine theta. That's trig. You can get that by making a right angled triangle right here, and then looking at what then this would be vx naught, this would be vy naught, and then you could do some trigonometry to figure that out. Alright, so we know this, and now again we're doing this without air resistance, so ax, acceleration in the x direction, will always be 0, and ay, acceleration in the y direction, will always be negative g, where g is just a gravitational acceleration at the earth, right? So using these equations, we could do some algebra, right? And then we could work out that the trajectory of this particle will be a parabola, negative parabola, like this. Could do that, and you can also do that when you have linear air resistance, but you cannot do it for quadratic air resistance, which is a good example of how as equations get more and more complicated, sometimes there are no ways to solve them analytically, and you have to use numerical methods like this simulation we're going to be writing. So while we could do the maths to work out exactly the path of the projectile, we're not going to do that. We're going to simulate it numerically. Alright, so let's talk about how we're going to do this simulation. So I'll just clear all this out. There's probably a better way to do this, but I'm completely new to this drawing software. Alright, so we're going to be using one of the core ideas of calculus. So let me just draw an x and y, some x and y axis, and I'll draw a curve. So this could be some curve y equal to f of x. Just an arbitrary curve, right? And then the idea of calculus is that let's just pick a point on the curve, and can I zoom in? Sorry, I'm completely new. Let's not mess with this software. Alright, let's just pretend we're zooming in. So if you zoom in at any point on this curve, the curve will eventually start to look like a straight line, and the more you zoom in, the straighter it looks. And then calculus tells us that we can then find the slope of the straight line that we see, and that will then give us the instantaneous slope at any point on the curve. Right? We're going to be, and that, that's just, saying that it's straight as you zoom in, it's just a fancy way of saying that if you vary x by a very small amount, the slope is pretty much constant if the change in x is very small. Alright, so let me yeah, this isn't going very okay. Let's write it down here. So let's say that in our simulation, the time goes from some time t to some time t plus delta t. Alright, now if delta t is small, or if it's approximately 0, then, that's supposed to say then, v of t plus delta t will be approximately equal to v of t. And let me put vector symbols in that v. Alright, and this is just a fancy way of saying that if we change the time by some very small amount, the speed pretty much stays constant. And this also holds true for the acceleration. In this case, we're going to have constant acceleration, so maybe let's keep that for when we have air resistance. But yeah, the velocity will pretty much stay constant for the duration delta t if delta t is very small. Right, this is the idea we're going to be using. So when t, let me get rid of that. So this is how we're going to do the simulation. So when t goes from whenever t goes from delta t, we're going to pick delta t to be a small number, right? Like in calculus, the way you would say it is you would say something like dv dt is the limit as t goes to 0 of v, delta t goes to 0, v of t plus delta t minus v of t all over delta t, right? This is how you would say it. That's supposed to be a delta t, yeah. That's how you would say it in calculus, right? You would use a limiting process. Well, in programming, we would just say, well, delta t is 0.001, or a very small number. We will approximate the limit by just saying it's a very small number, right? That's the core idea. So t goes from t to delta t, where delta t is small. So then what are we going to do? So first is to say that the position x, or the x position, is going to go from the old position, which was just x, to x plus vx of t, where vx is the horizontal speed, times delta t. Alright, and this is assuming that vx, if vx of t is constant over the time delta t, then this works. If it's not constant, you would have to put an integral symbol, but if as long as we assume delta t is small, this thing is pretty much constant, so this works out. Then second, we say that vx goes from the old value, which was vx of t, to vx of t, or let's just put vx, since we put vx over here, vx plus ax of t times delta t. So the speed is going to change by the acceleration times the change in time, as long as this acceleration is essentially constant, which it will be because the delta t is essentially constant. Right. So as long as we have a formula for this a of t, we can do this. So for no air resistance, we have a formula for ax of t, right? Because it doesn't depend on t, it'll just be constant, 0 in the x direction and negative g in the y direction. Of course, yeah, here we did for x and x. Obviously you would do this for x and y, right? Now for linear air resistance, we will see that these formulas will not depend on t, they will depend on v. But that's fine, because at any point in time we also have the velocity, so we can put the velocity in here. So if you like, instead of writing ax of t, we might write ax of t v, like this. So it could be a function of time and speed. Right, that would also work. Alright, so I think we're ready to write some code and try to implement this. So let me go to the right folder. Sorry, I'm in the wrong folder. Let's see, projectile motion simulation. And I'll make a new folder here. Call it episode 1, because this is episode 1. And I'll open up my favorite code editor, which is Visual Studio Code. So let's make a new file. I'll call mine just main.py. And let me bring up my terminal and clear it out. Alright, so first we need some constants, right? We need to know the initial speed, which I'll denote by v, and we'll just default it to 20. We need to know the angle, which I'll call it theta, and I'll just default that to 45. And we also need to know the terminal velocity, which I'll default to 5.65. So we don't actually need to know the terminal velocity yet, but we will when we implement linear and quadratic air resistance, so I'll just keep it in for now. We're also going to need matplotlib, so I'll import that. Let's see if I can spell it. Matplotlib.pyplot, and I'll call it plt, as is traditional. And I'll also import math, because we will need that. Yeah, actually, let's make this radians. So that'll be math.pi over 4, like that. So later on, we will have inputs that will come up that let us input these values. For now, I'll just keep these like this, like these default values. So we're gonna let's make a list for the things we need to keep track of. Let's go back to one of these plots. Let's pick this one, maybe. Right, so you see that we're plotting horizontal displacement and vertical displacement. So those are the things we need to keep track of in a list. I'll make a list for x coordinates, big X, which will start as an empty list. And I'll also make a list for y coordinates, big Y, empty list. Let's make a variable to keep track of the x coordinate, which will start at 0, and one for the y coordinate, 0. Let's make one for keeping track of the horizontal speed. That'll start at v times math.cos theta, and vy will start at math.sin theta. We're not going to make variables for the accelerations because we're going to have functions for those. I guess maybe I'll just define them up here. So ax, start with that. I'll call it an underscore x. Why not? Alright, so ax, that'll just be 0 for now. Alright, ay, that'll be negative g. Oh, we didn't define g. We need to define g. So g is 9.81. And I'll just tidy this up to make this look a little nicer. If we grab all of this and move it down here and get rid of this line break, we have all the constants in one place, which looks better, I think. Sorry about that. Alright, now we need a loop because we're going to be computing many coordinates, right? So to start with, we'll just do a for loop with a set number of iterations, and then we'll go from there. We also need a time step. That'll be essentially the delta t from what we were doing on the over here earlier. This delta t, it needs to be small. I'll call it time step. Alright, so let's just call it delta t, or delta. Let's call it delta 0.001. So now we need a loop. I'll just do from 0 to, let's say, 3000. So what do we want to do inside the loop? This is when t goes from t plus delta t. Well, we talked about this. Let's go back to the drawing board. So first compute the x coordinate. All right. So x is going to be x plus the horizontal speed, which is vx times delta. And the same for y. Y will be y plus vy times delta. And I'll just add in a little comment to explain what's going on. So calculating new position. And let's calculate the new speeds now. Calculating new speeds. So vx will be vx plus ax times delta. And vy will be vy plus ay times delta. Whoops, that's not a plus. There we go. All right, and now we're gonna add x and y coordinates to x and y lists. So this is a common naming scheme you see me use. I have x and y in lowercase for the coordinates, and uppercase x and y for the lists to store the coordinates. So we'll do big X dot append x and big Y dot append y. Alright, so now we have a list of x and y coordinates. We can now plot it using matplotlib, and that's super easy. We can just write plt. PLT is from up here when I called it PLT. So plt.scatter, which will make a scatter plot, and then give it x equal big X, which is our list of x coordinates, and y equals big Y, our list of y coordinates. And then I'll write plt.show, which will show the plot. So let's run it and see what we get. Whoops, misspelled it there. Right, so you see we get this. So it doesn't quite look like a parabola, but I suspect what's happening is that we're simply simulating too far into the future, because we haven't told the simulation that, you know, when there's a solid ground. So when the y coordinate goes to 0, it's not going to stop. It's just going to keep going negative, which I suspect is what's going on here. So let's try to make let's try 30 iterations only rather than 3000. Let's see what that'll look like. Okay, it's looking kind of like a straight line now. That's probably because we don't have enough iterations. So tell you what, let's try 300. Alright, now it looks a little bit more like a parabola, but it's still going negative. So what we can do is we can make this delta t a little smaller. Because if you think about it, let me just bring up a calculator to illustrate what I mean. If we want to know, if we want to know how many units of time into the future we're simulating, we can simply take our delta 0.01 multiplied by the number of iterations, which in this case will be 301, and it's 0.301 seconds. So if you by making delta t smaller, you're also decreasing the amount of time that you're going to be simulating for. It still looks like we're going negative, quite negative. Let's make delta t even smaller. Now it looks kind of like a straight line, so we might need a few more iterations. Alright, now we're getting somewhere. Let's try maybe 2000 iterations. Then it goes negative, so that's too much. Let's try 1500 iterations. Yeah, now we have a nice looking parabola. Alright. So you saw what we were doing here, trying to find the right combination of delta and number of iterations. That was kind of a pain in the ass. So this is why you don't use the for loop for this. I was just doing this for illustrative purposes. But think about this. A for loop, you're saying, I want to do this number of iterations. But that's not what we want for this problem. We want to say, okay, we're going to start simulating at time 0 and then stop simulating when it hits the ground, right? We want to make sure that we get to the point where it hits the ground, but we don't want to simulate anything else after that. So for that, we can use a while loop. So let me get rid of the for loop. And what are we going to say? We're going to say while y is, where's the symbol there? While y is greater than or equal to 0. Right, because you see here, we're updating y every time in the loop, and eventually y is going to be negative, and then it'll stop. So let's see what we get when we do this. There we go. See? That was the perfect number of iterations. Now, we cannot say while y is greater than 0, because you see we're starting the y out at 0. So if we try this, nothing will happen. So it plots nothing because this while loop wouldn't run the first time. So it has to be greater than or equal to 0. Like that. So yeah, that actually tells us what we need to know. This is how you code a projectile motion simulation for no air resistance. Now, we didn't do it for very long. No, sorry, I was thinking of something else. Never mind that. Alright, sorry, I accidentally hit the stop button on my recording. Let's just bring this graph up again. So the reason I was getting a little confused is that I saw how small the numbers were on the y-axis. I found the problem though. So the problem is right here. It's just a typo. So Vx is v.math times cos theta, which is correct, right? But I then have Vy equals math.sin theta. I forgot to multiply by V. So now let's try it. There we go. Yep. Now this is looking a lot more reasonable, the numbers and everything. Alright, let's just add on some axis titles. Or the video is already getting kind of long. I guess we can do that in the next video. One more thing before we end this video. I want to show you what happens if we change the time step. Let me close that. So I have a delta of 0.01. Let's change it, make it much smaller. So it'll take a little longer this time. Boom. You see, it's the same curve. It's just a little smoother because there are going to be way more points here now. Now let's try and make delta t much bigger. Let's try 0.1. Okay, it still kind of looks like a parabola, I guess. Let's try delta equal to something like 1. Yeah, so we're just missing a bunch of data here. Okay, so we didn't quite get the problem that I was looking for. Okay, I'll give you another example. Let me draw, open up Smooth Draw, and I'll just open up a new template. Very professional, I know. And let's get rid of that. Alright. So the thing I want to get at is that, let's say you were writing some other simulation. You got a charged particle right here. Or it doesn't have to be charged, whatever. 2 particles, right? When they're far away, they repel. But when they're close together, they attract. So, and now let's say the thing that happens in real life is that these things are moving towards each other, but they're repelling, right? So eventually they just repel each other too much, and then they go each other's ways, like this, right? But if you make them go really fast, yeah, this is a masterclass in drawing, I know. If you make them go really fast, then before they have a chance to turn away from each other, they get close enough that they start attracting. Yeah, I don't know what's going on with this drawing. It's probably just confusing you. Yeah, eventually they actually get close enough to start attracting, and they combine together, sort of like a chemical reaction, I guess, right? And let's say you're simulating this, but you make your time step really big. So then you have one point in time where the particles are here, and then you know, in order for them to start attracting, let's say this is the maximum distance, right? So now if your time step was small enough, maybe in the next frame they would be here, and they would be attracting. But you made your time step way too big, so in the next frame they've actually passed each other, and they're now here, and they're repelling. So they just move past each other, and because your time step was too big, you weren't able to capture the moments in time where they were retracting, so you missed the entire effect, right? That was my point, that you need to make sure that your time step's small enough. It doesn't look like we really missed out on any effects by making delta big. We just didn't get very many points. So let's put it back to, I think we had 0.001. Just, yeah. I'll put it back to how it was. Yeah, so this is the graph we get now. Alright, so I guess in next in the next episode, we can try to include air resistance. We'll also probably clean up the graph a bit, add some axes, titles, and stuff like that. So I'll see you then. Oh, I hit the